Hello everyone and welcome to today's webinar on understanding of IC standard of CT maintenance. My name is Sanjay Yadav and I'll be hosting this session today. Speaker for today's session is Mr. Ali Hussain, who is an application engineer at Mega Middle East. So before handing the mic over to Mr. Ali, I would like to highlight a few points. You all are being muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session. We also have a Mega exclusive page on social media on Facebook and LinkedIn. I'll just share that in the chat section. You can go there and you can follow us for regular updates. We also have a lot of upcoming webinars in 2021. I'll just share that link in the chat section. So you can go there and register yourself for the upcoming webinars. There will be a small survey form at the end of the webinar, so please do fill the same for the feedback regarding the webinar. The recording will be sent to you in 2 working days through the GoToWebinar system as a standard process and also along with the certificate. And I now hand over the control to Mr. Ali. So let's get started. Over to you, Ali.
Thank you very much, Sanjay, and welcome everybody. Wherever you are. Today's session is about CT testing, and I have a quite full of the session, to be honest with you. And as usual, I always include in my session some practical things. I have my camera set up here with me, and a full setup, and a CT, and a CT tester from Megger that we will talk about very briefly. I would like to remind you that if you have any questions, please feel free to ask them in the question section. It will be my pleasure to help you answer these questions, and I hope they meet your satisfaction. So please stay with us throughout this session. At the end, we will do the practical part as usual. So for our agenda today, since we are talking about IEC standard from perspective of CT testing, I will have to speak briefly about IEC standards, what standards available, what classification based on these standards available, and for what purpose. And then we will go through some of the testing techniques that has been usually done in the past, or what we call conventional methods of testing for the CTs, what used to be done, and what is the you can say advantages or disadvantages of using these conventional methods. And then we will talk about the new methods that Megger introduced to the market from testing, the innovation in these testing, how can it help you make your testing easier, better, faster, safer to you as well. And then we're going to talk about some of Megger solutions, and at the end we will do, as usual, a practical demo on a CT I have here for me. Again, I would like to remind you, if you have any question, anything at all, please feel free to drop it in the question section. So without further ado, let's start with a brief fundamentals about IEC standards. So there are usually 2 old standards and 1 new standard that been used for CTs. The standard is itself defined by the IEC 644, either -1 or -6. -1 is for the general CTs standard. We'll talk about the classification in this standard briefly or in details later on. And then we have the -6 part of it. It is more focused on the transient condition current transformer, the classes TBX, TBY, and TBZ. Talk about that later on as well. Both these standards are, you can say, obsolete now or old. You might find them still mentioned on the nameplates of older CTs, but most of the new CTs that come is according to the new standard, which satisfy more applications. It is the IEC 61869-2. This international standard cancels and replaces the both all the standards, the 644-1 and 644-6, and it does comprehend both of these requirements, the standard CTs and the transient condition CTs as well. You can test the older standard TC using this standard as well if you would like to do that. So just a brief introduction about the circuit diagram of CTs. If you look at the CT, it's a device that we use to transfer the current from a high primary side, usually a line or a feeder going to a line or transformer or coming out of a generator, etc., etc., and then minimizing it to a standard secondary currents, either 1 ampere or 5 ampere. This is the usual values used around the world. Now, for an ideal CTs, you will have a primary side, you will have a primary side IB, and usually this primary side is the primary conductor and certain types or certain physical shapes of a CTs like window type or bar type, and usually it's a one turn, and then you have a magnetic core that will define the characteristic of that CT, and then a secondary core with number of turns to reduce the current to either 1 or 5 ampere. However, in the real world, there is no such thing called ideal CT that will give you an exact approximation of your ratio between the primary and the secondary. There will always be errors and losses in these CTs, and this is what you will find in the field, something with a ratio, transformation, and also an errors. These errors define for us, or this is what we want to verify when we're doing testing for CTs. We want to make sure that these errors is within check, within the specified values set by the standard or by the nameplate of the CT, and that for that we do number of tests to these CTs, and these errors does create the fundamental or foundation for the classification of these CTs based on the standard. So the starting of the classification of these CT errors start with the application of what the CTs will be used for. The first application is metering application, when you want to connect them to energy meters or even power quality or just a general voltage current meters for this instrumented transformer. And this metering CTs, usually the application is when you are working within the nominal range of the CT. For example, if you have 1000 to 1 CT, you will be working within this range from 0 to 1000 ampere on the primary side. And you want to have as much as possible accuracy within this range, because especially for energy meter, any errors coming from the CT sides will directly transfer to losses in profits or metering revenue and so on. So it's a direct money loss or direct energy not counted for or counted for, depending on what the error value is from the CT. That's why it's very important to check the accuracy of metering CT, and the standard does specify the application for this or the classification for this metering CT based on accuracy mainly. The second application we have for the current transformers is protection systems. The protection systems usually don't operate in the normal conditions or normal values for most types of faults or unusual conditions. Usually they operate in the fault condition, which is number of thousands of kiloamperes, or number of times, 5 times, 6 times, 10 times of your rated current. So their specified range is usually in the above your rated current range. So I need some accuracy, not that much, some accuracy that I can work with in the fault range condition without spending too much money on my CT or too much resources on it. So the classification of protection type CTs is based on this requirement, having a high range of acceptable error, like 5% or 10%. It's also considered as an acceptable error in protection system, and also compensated for in the setting of the protection systems itself. So starting with the first application, the metering application of the CTs, the most important thing for me is the ratio and phase displacement error is to be not exceeding a certain value defined by the standard, and the classification is based on this error itself. And usually the range for it is from 25 to 100% of your rated output. For example, if you have 1000 to 1 CT, from 200 to 1000 ampere is your rated, or the most accuracy you will get in this range. Although there are some special cases or special classes that can give you a higher accuracy at lower percentage rated current. So in order to summarize most of the classes that we have in IEC standard, I am focusing mainly on the latest version of the IEC 61869. I will not consider the two older standard, as this one already cover both of them. This table comprehends most of the classes. We have 6 classes. This accuracy class represent the percentage error accepted at 100% of the rated current. So this is 0.1% accepted error, plus or minus. This is the first class, and it defines not only the ratio as an error, but also define the phase displacement, because the phase displacement between your primary and your secondary is part of your ratio. And so that's why the standard also define a maximum error for it at that classification. So for example, I have 0.1% accuracy class. At 100% of my rated current, my expected error should be plus or minus 0.1. If I go less, for example, up to 20 or down to 20% of my rated current, my accuracy class can, or my accepted accuracy can go up to 0.2%, which the standard accepts at a lower percentage of your rated current. Also, if you go up to even 5% of your rated current, let's say 50 ampere out of the 1000, in our example, up to 0.4% accepted from your magnitude ratio. And as for the phase displacement, we have 2 methods of representing it. We have minutes, which is basically each 60 minutes is 1 degree. The phase displacement between the primary and secondary is up to 5 minutes, means 5/60 degree is accepted. Or either I can define it by centiradians. This is another unit can be used or found on some CTs. It's accepted to this much percentage. So when I want to do testing for the ratio, I have to consider both my ratio as a magnitude and also my phase displacement. Another classes here, we have 0.1, 0.2 classification, 0.5, and 1% classification. As well, there are 2 special classes, 0.2s and 0.5s. These classification give you a tighter, or you can say a lower error range within the lower rated percentage range as well. So here at the 5% rated current, my acceptable error is 0.35. So when I have a low current in this CT, it should give me a higher or better accuracy at lower currents as well. This 0.2 is compared to the normal 0.2, which the accepted error 0.75 at 5%. The 0.2s and 0.5s give you a better accuracy at a lower range as well. So when you're testing any metering CT based on the IEC, this table you have to refer to it once you finish the test to see whether your CT, according to its classification, is passing or failing. And from what you see here, you don't need to just test at the rated current, but you need to test at a percentage of that rated current. For example, at 100%, at 5%, or at 20%. So a lot of measurement required to test based on the standard itself. Another thing that the standard that define or introduced to metering CT is something called security factor, or FS, Factorion security, with French translation. This factor, it's implemented or used to protect the meters during faults. So when I have a security factor or a value of FS, usually 5 or 2, it means that at this number of times of the rated current, the meter or the metering CT should saturate, meaning that it should not be able to transfer the primary waveform to the secondary side. This saturation will not allow the meter, connected meter to this CT, to read the fault currents, usually happen during fault currents, and thus will protect the meter from any damages or high voltages during these faulty conditions. And even though it's something new and maybe not everybody do testing for it, it is important, very well important for the protection or for the safety of the meter connected to this CT. So it is something also required to do testing for, and it's usually related to what we call the knee point of the CT. This test is very important once we want to verify this security factor. For the protection CTs or protection classes, there are 4 dominant classification or common classification that you might find out there based on various IEC standard, but the IEC, the latest one, 61869-2, cover all of them. First, we have the B class, which is the most common available in the market. You'll find it everywhere. You will find it in transmission, distribution, circuitry, and secondary and primary distribution available as well. Then we have the BR, the low remanence classification of the B class. And then we have the TB classes, TBY, TBZ, TBX. These classification, the T represent the transient behavior allowed in these CTs, as we will see later on. And last, we have the BX, you can say free selection class, where you can define, you can say something with certain parameters, define a certain class for your specific application. We're mainly going to focus on the first 3, as the fourth one is more of a free Roman specific classification. The people who work with the IEEE, they might understand this as the X class in that standard. So starting with the B classification, the standard specify the error, the phase displacement, and also accuracy limiting factor. That's very important thing. So this is couple of classes in this classification category. For example, I have 5b means I have 5% plus and minus 5% error, and here you hear me say 5% error, which is something very huge or big compared to what we had in the metering CT, 0.1, 0.2, 0.5 in that classification application. But in reduction CT, I can go up to 5%. There is no problem with that, but at the accuracy limiting factor. So I should have plus minus 5% at my defined accuracy factor. For example, if I say I have 10B20, means I have plus minus 10% error, but at 20 times my rated current. So when I have a CT that is 1000 to 1, at 20 times that, that's like 20,000 ampere or 20 kilo ampere. At that value, my acceptable error is plus or minus 10%, which is give you the range of huge range of good error for us to do application purposes, protection purpose. And this is the most dominant class that you will find on most CTs out there for in the field for protection classification. The next classification category we have is the BR classes. It's similar to the B classes, just that the R represent a low remanence, meaning that when this class or when this CT get saturated or reach its saturation value, that once we turn it off or stop that, it will not the remanence in it, the magnetic remanence when the core get magnetized should not exceed 10% in the CT. And usually they are using some air gaps to achieve that in these CT. There are some application for these CTs. So and this 10% is always defined in this CT. So you will find an accuracy limit like the 5. You have the ALF, and also a third factor is the remanence value as well specified on this CT. So this is something you have to consider as well when you have a PR classification. You need to test it based on this as well and find out that your remanence is less than the specified value once you do testing for this CT as well. The next classification that we have is the transient condition or TB classes, which usually have 3: TBX, TBY, and TBZ. These classification are designed when you have transient conditions, like having AC and DC currents during a fault for a specific duty cycles. For specific cycles, you'll have this. So these CTs can give you that and can transfer that waveforms efficiently for that application. We have 3 classification for that. We have TBX, TBY, and TBZ. And when you go to any of these 3 classification and this type of classification, you will find a lot of parameters. For example, TP, TS, the symmetrical short circuit current factor, and so on factors. A lot of parameters in these CTs. We can test that very easily with one of our testing solutions, as testing them using a manual or conventional method will require you to do a lot of calculation really to be able to test these specified parameters on the nameplate itself. Just to give you a better picture on this, we will compare the normal B class to these 3 TBX, TBY, and TBZ classification, and this is the picture of the BH curve, or what we call core curve. You can see here that you have for the TBZ, TBY, and TBX slightly higher values for remanence required to saturate their cores. For the TBZ application, you can see it's very linear when you move at higher flux densities. And also the remanence value for it, it's almost negligible. So whenever use it, it will not have a huge remanence in it. It will demagnetize very, very easily for that. As for the other two, TBX and TBY, have a slightly or much more actually than the normal B classification. So they usually used in the applications where this characteristic is required, something like auto recloser application, when you have number of turn on and off cycles and the fault could be persistent. This classification is recommended for that application. Or for example, when you have generator protection and the fault currents there are very, very high, can go up to 60, 70,000 ampere. The saturation of a normal B classification will be required for that will be something very, very big. But if you use these transient classes of CTs, you will be able to achieve that with a smaller size CT. The last classification is the BX classes. These are more of something defined. You have to define each and every parameter for them. It's more of a free roaming for a special application. So what does a nameplate based on IEC specification looks like? It's something like this. This is an example of a nameplate. This nameplate does have two cores. First core here, it's this table, this line, it's 150 to 5 ampere, the ratio. And then you have the terminals for it, 1S1 to 1S2. This is the first core, we call it. The rated burden to it, so you cannot exceed this rated burden to achieve these classification here. And you have here the class. This is 0.5, indicating that this is actually a metering CT, not our detection one. And also this is the FS, or what we call the security factor for this protection or metering CT. And then the second core we have it here is also the same ratio, 150 to 5, and these are the terminals for it. And also the rated burden for this CT. And the classification here is the B classification, 5B. You can see that this 5B have an accuracy limiting factor at 10, means at 10 times my rated current, my error should not exceed 5%. So when you go to any nameplate of a CT and you find something like this, like the B classes or even the terminals defined as S and the CT, you will know that this is a CT based on IEC standard. And you should know what each value means. For example, the ratio, the rated burden, and also the classification. And the classification is very, very important because this is what you're going to assess your saturation test, what we usually do with a high voltage source test, as the classification can be verified through the test. Other information here indicating, for example, the frequency, the voltage level that this CT can work with. This is CT is in the medium voltage level and distribution that can go up to 17 or kilo ampere or kilovolt. So, and usually in distribution system they have a combination of two CTs or two cores on one enclosure that give you one protection and one metering CT at the same time. Both of them share the same primary. This is another class B CT. It has a different classification. Here you can see the classification 5B10. The ALF is 10 and my accepted error is 5%. The rated burden, you can see the CT ratio 300 to 5, and also in this CTs, the standard itself is already defined on the nameplate of the CT. If you want to know that your CT is based on IEC, the easiest method for you to do that is just look at the terminals. When you see S and B for the primary and S for the secondary, this is usually going to be an IEC standard CT. The IEEE usually they use H and X value to define that. So this is some information briefly about the standard and what does it define on the CT. Now we're going to talk about testing. What is the conventional methods of testing for the CTs, and what the new methods that we can use for testing. So starting with the conventional testing practices, the most standard test, or what the standard does define for you, is this number of tests. You test the insulation resistance, basically the integrity of your insulation in your CT, since this CT will be connected on a primary that have high voltage on it. So usually you'll do it for the primary side, the secondary side, and between these two-sided primary and secondary. Then you have the winding resistance. The winding resistance is a very important test for calculating the losses, or if you have a problem with your windings, and also calculating your ALF value, or accuracy limiting factor value. Then you have the excitation test. This is what we refer to saturation or knee test for the American standards IEEE. This test, in combination with the ratio errors and winding resistance, can give you your ALF or classification for your protection CTs. Then we have the ratio and phase deviation, and it's very important that I also include the phase deviation in my ratio, because it's actually part of your ratio, this phase deviation between your primary and secondary. And then we have a polarity test. This is very important when you are dealing with differential distance or directional overcurrent relay, as the polarity will play a huge role in there. But also in metering application, the polarity will define to you, especially in the new smart meters, where they can see exporting or importing energy. And then last but not least is the burden test. This test is not defined for the CT itself, but to the burden connect to it. You need to measure the burden of that device, and not only the device itself, but also the lead. And it should not exceed the specified burden of the CT. Otherwise, your CT will not work as per specified. So starting with the first test, insulation resistance. Insulation resistance test is a basic test that you do for all electrical equipment, or what we generally known. This test, you usually do it between primary and secondary, primary and ground, and secondary and ground. When you have window type CTs, usually you don't have to really worry about the primary sides of your CTs, since this CTs does not really have a primary. The primary is the cable itself, or the conductor itself, and that you're already going to test it during the cable testing or commissioning for the insulation. So usually in this window type CTs, you will only do secondary to ground. And one important note about this test is, if this test fail, you don't really have to continue do all the other tests, because the CT need to be changed. Don't bother even continuing with this all other tests. So usually start with this test. That is very important. Some other people CTs, they might other tests as secondary, or sorry, then anything below like let's say 10 mega ohm or less, it's something considered questionable and required some maintenance. Meaning from someone here stating that I have issues with my microphone. Is my sound very clear or not, Sanjay?
It is clear.
Okay. If there is any problem, please tell me that, so do not go off and continuing and nobody can hear me. Okay. So the next test we have is usually once we finish the insulation resistance, we'll directly go to winding resistance. And it is important to start with the winding resistance test rather than starting for the ratio or the core or the saturation test. The reason for that is because once you take off any CTs, there are some remnants in this CT, or what you call a small magnetization in the core for it. So when you do ratio test or when you do saturation test, this two test, if you directly do them to your CT after disconnecting it or taking it for maintenance, it will be affected. It will not give you the actual value. But if you do winding resistance test first and you fully saturate your CT, because this test, let's face it, it will inject a DC current on your winding and it will saturate your core. This test will give you the winding resistance value. Usually you will have to correct it to a certain temperature value. It is very important to have a low resistance, meaning a low losses, but not lower than the factory accepted value, indicating that there is some short circuited, or not very high resistance value, meaning you have a bad contact between the tab or any interconnection inside your CT winding. The reason why this test is conducted usually first is because it will saturate your core. Once your core is saturated through this test, you'll have to do something called demagnetization. Basically, your core has been magnetized. Since you injected a DC current on it, all the molecules has been magnetized to a certain level. This magnetization, you do a process to it called demagnetization to remove this and create the similar random pattern of magnetizing molecules in this core. There are different methods to create this CT demagnetization. Usually, some people use variable voltages at constant frequency, or they just decrease or increase and decrease the DC alternating currents. So they inject a DC to fully saturated in one direction, then inject a DC to partially saturated in the other direction, and so on and so forth to achieve that small remnant. So they start at this value, this place, and then they inject a DC current in the opposite direction to go on the other direction. Then they increase or inject another DC the other direction, but with a lower time, and so on and so forth until they reach the you can say very low remnants magnetism inside the CT. It is very important to do this in order to be able to do the other test after the winding resistance test. Then we have the excitation or saturation test. In that order, we first start with the winding, the demagnetization, and then we do the excitation saturation curve, or what you call knee point test. This test is usually using an AC voltage from the secondary side, where they apply this to the CT winding on the secondary side and measure how much current this AC output is giving while the primary side is open. This test will confirm for you the accuracy rating, especially for the protection CTs, and also will put some stress on the winding itself to check if there is any shorted turns or so on. And usually this test is done to a certain level, so some CTs can go up to high values, up to 500, 600, 900, 1000, 2000 volt AC to be able to saturate the CT. Saturation means you reach a level where the current increases rapidly with the small increase of your voltage. And usually this test is given by a graph as well. For example, this graph here showing you a different saturation level. Once you reach your saturation point, defined by this point, the small increase in voltage will increase the current drastically drawn by the core, meaning that in order to push the waveform to the other side, you have to push more current to the core because the core has been saturated. That's why they call it saturation test. Then you do the ratio test, ratio and phase displacement. Now, the ratio test can be done by two methods. You either go to the current method or with the voltage method. The current method is basically will get a variable current source where you can inject the high currents at different percentage of your rated CT current value. Usually this will require you to have something very heavy and expensive current source that can give you in terms of thousands of hundreds of amperes to be able to do that with the current method. The other method is to do it with the voltage method, where we, instead of inject current on this CT, we inject a voltage from the secondary side to the primary side and measure the voltage in the primary side. This voltage measurement or voltage method requires something very small. You don't have to really have very high value for voltage to be able to get the ratio very, very accurately. And this voltage ratio, you can use it through some modeling to be able to calculate the different rated current values at the rated different rated burdens. There are some models for that you can use, and usually will give you a tables like this. If you do that voltage ratio test, you can then from that ratio at the rated current value, you can get the error directly at different rated currents. This is very, very important when you're doing metering CTs to check the error at different rated currents. And not only that, if you also you can check with different burdens. Some people use a burden box to change between the burden, but really you can do that through modeling of that ratio at a certain value and then calculating the other value as well. And not only the ratio, but also the phase error as well. Then we have the polarity test. Basically, it's to test and verify the polarity between your primary and secondary. Usually, this is done through measuring the phase angle, the voltage phase angle between the primary and secondary, and checking whether it's something near your 0 degree range or 360 degree range, or it's something within the 180 degree range of phase deviation. If it's 180, then you have the reverse polarity. If it's 0 degree, then you have the correct polarity. And last, the burden test. It's something done to your relay or to your meter. We basically inject a small AC current, usually the rated current of that input, 1 ampere or 5 ampere, and measure the voltage drop across it. And from the voltage drop and the current, you can calculate the burden as a VA value and an angle as well. It's very important to get the burden connected to your relay, especially if you have electromechanical relays, you need to make sure that the rated burden of that relay is less than the rated burden of your CT. Otherwise, it can saturate your CT very easily if it's above it. Now, this is what's already been done or been doing in the previous testing throughout the years. These tests are what everybody already is doing nowadays. So what alternative methods or testing techniques that Megger can provide for you to make these tests even easier or simpler or safer for you, especially for the saturation test where we require sometimes very high voltages to do that test? How can we make that a lower value using clever and smart methods? So the first thing about CTs, some of them comes in multi-winding. When you before want to test these CTs, you usually either will have the test equipment do the test between two tabs and then change to the test between the other two tabs, and so on and so forth. So to test a CT fully, you will just have to test a lot of tabs, repeat the test multiple times, 5, 6, 7, 8 times, depending on how many tabs you have, in order to test all these tabs. And that's a tedious and a long process to do. Testing one by one, we call much more timing for testing. This is what we call non-concurrent method. With the new designed or new used methods from Megger, we can give you the testing of all these tabs, up to 5 tabs, simultaneously. So you have multiple meters and multiple and one injection output, and you can measure all these tabs at the same time, thus shortening your test time very, very drastically. And the accuracy for these tests are very, very good. And not only you can test between one tab and the others, but you can test also between the other tabs themselves. So this is an example where you can test from S1 to S2, S3, S4, and S5, but also you can test between the inter tabs as well, S2 to S3, S2 to S4, S3 to S5, and so forth and so on. And all these tests will be done simultaneously. So saturation test will be doing all the tabs at the same time. Then the ratio test all the tabs at the same time as well. And this is some comparison between the two different methods. The concurrent method, this where we do all simultaneously, and non-concurrent method. For example, for the winding resistance, the values are very similar to each other, very minimum difference between them, between the non-concurrent and the concurrent method. Also, this is values done for the saturation test, which is something required sometimes high voltages. Also, you can see it done with the concurrent method as well, giving you a very accurate result. This is saturation, another view of the saturation test doing concurrent method. This is done only in 2 or 1 minutes, and so on, using a Megger concurrent method. Another thing or another issue, especially in the saturation test, is the high voltages component. Sometimes you have very high voltages on the CTs. You have to inject them to get this saturation value, and sometimes require you something either unsafe or high voltage source, which could be expensive, and also unsafe for you to use. That's why Megger has developed a method to overcome this issue. One method was used and still being used as well to overcome this issue is using an AC method, where they, instead of injecting the rated frequency of the AC, they reduce the frequency to a very low value to be able to achieve that saturation, and then interpolation the value at that frequency to your rated frequency. This method helps a lot in doing that, but the method that Smigger is using is called the DC method, where we're using a low DC method on the core to saturate it, but instead of increasing the voltage to reach that saturation value, we just give it for a certain amount of time. Based on that certain amount of time, the accuracy or saturation value will be calculated. How much time do we need to reach that saturation in the DC can be calculated using some integration methods to get the AC saturation voltage, and it really works very, very fine. If you want to compare it between the AC, the normal AC, and the DC method, a very small error difference between them. It will give you a safer way, but also will give you the ability to test very high voltage saturation CTs, especially for the transient TBX, TBY, TBZ CTs at a very high voltage using a very low voltage to get that saturation value. All of these advantages that you can get is included in our MVCT and MRCT solution. Both of these solution can give you these advantages in testing your CTs. And giving you the ability to have a CT tester that is very compact and cheaper than the conventional method. We require multiple test equipment to do that, and some of them are heavy, bulky, manual usage. They require high current leads or high voltage leads, heavy to connect and do all these. These two devices eliminate most of that for you. Starting with the MVCT, the device called MVCT, meaning meager voltage and current transformer tester. It has the ability to test both the VT and the CT. For our today's session, is we are only mainly focusing on the CT itself only. It has easy to use one button automated test plan. You just put the nameplate data and it will choose the parameter for testing automatically for you, and also give you the patent concurrent method where you test simultaneous tab. And I do emphasis here on the tab word, not cores. You cannot test multiple core at the same time, only multiple tabs simultaneously. When you have multiple core, you need to short the other core to test the first core. But if you have multiple tabs on that core, you can test all of them at the same time using the concurrent method. It has the accuracy required in the current and voltage source embedded in it to test metering and protection CTs as well. Especially for the metering CT, it requires very high accuracy in testing. The MVCT can do that for you. For knee points, it can give you up to 30 kilovolt knee point measurement value using the DC method. So if you have this bulky huge CTs that have a really huge or high voltage knee point value, we can get that using the DC method. Also, for VT testing, it does include the winding resistance, demagnetization ratio, and phase deviation, and knee point for the VTs as well, but only for the inductive VTs, or what we call IVT. The capacitive VTs are not being able to be tested using the MVCT. And also, they give you the ability to do secondary burden test for meters or protection relays. As an optional thing you can add is to have an integrated 1 kV DC insulation, but from my recommendation, if you can use your own meager insulator or meager tester, like the 5 kV or 2.5 kV, you can use that as well. This is just an optional thing. And also you can add an optional thing to do single phase relay testing in the MVCT as well, if you would like to do that. Then you have the bigger brother, you can say, to the MVCT, the MRCT, stands for multi-ratio CT testing. This tester give you combination, a hybrid combination between having the DC method for the saturation and an actual conventional AC method up to 2 kV. So if you want to do the actual AC saturation test, you don't want to do the DC one, to get the extra accuracy. For that, you can go up to 2 kV with this MRCT. This 2 kV source not only give you the ability to test the CT using the AC method, but also give you the ability to test CVTs, or capacitive voltage method, because the MVC or MRCT can test VTs as well. Can give you the ability to test CVTs, doing the ratio for them, and also have the other options for the MVCT, like the insulation resistance and the single phase relay testing. Both devices can come with a screen, integrated screen, to give it full on standalone configuration. You don't need a laptop to control it, or you can have it without the screen to lower the cost of the device and use a laptop to do communication and control for the device. Both of them have that option as well. So some of the things to highlight in the MVCT and MRCT is the nameplate guessing. If you, for example, want to do, or you don't have a nameplate, you just give it the standard, any information that you can gather, and it will guess these values for you for the CT. Of course, it does have some limitations since it's a guessing function. So no assessment will be done. It will not give you pass or fail based on this assessment, because this is guessed value. And also, once you finish testing, all the reported, if you have the integrated screen or the laptop, will be automatically generated for you, or the graphs or the tables. And also the assessment, whether it's pass or fail based on the standard selected, will be given as well, making your job much easier when you're testing these CTs. It has a very informative screen that will show you all the connection, how to do the connection based on the selected specification and rate value of the CT, and based whether you have the IEEE or the IEC standard, the connection diagram will be changed to that. So at the end, I will do a quick demonstration of the MVCT. I have it connected here with me, and I have a CT. I will do a quick test by it, showing you how does it feel or look like. If you want more information about that, you can contact me and we can arrange something later on, one-on-one ourselves. So for my testing today, I have this CT. It's a 5B10 class CT. It has a ratio of 300 to 5 and a class of 5B10 at a rated burden value of 5 VA. And it's defined based on the new standard IEC 61869-2. So we are going to test the ratio, the class, and the winding resistance. And also I'm going to throw an insulation resistance test at the beginning of the test as well. So let me turn on my camera and start the test. Turn off my screen, and you can see my camera. I have the MRCT and the CT already connected for us. Might have to turn off the light to be able to see the screen very easily. A second. Yes. So I will zoom in first on my MVCT, and I hope everything can be seen very easily on the voice. And also, let's verify our CT that we have here. It is a 300 to 5 5B10 CT, and 5 VA burden CT. So let's start by going to our MVCT here. This is the optional touch screen. You can do without the using of a touch screen to do testing of your CT. And if you have any question, please feel free to ask this question as we can go through a quick demonstration. So when you want to start any test in the MVCT, the first thing you need to define is the nameplate of your CT. Before going through any test that we need to do, we go to the third icon at the top here, click on it, and click on the nameplate data. The first thing we need to do is to define the nameplate of our CT. For example, in this test plan, I can add more than one CT. That gives me one report, so I can define the number of CTs. If these CTs has multiple cores, I can define how many core per these CTs, and then for each core, I can define how many number of tabs. So for my CT today, I have only one CT, one core, and in this CT, I have only 2 tabs. So I'm going to click here and select 2 tabs. Then I can give some labeling information for this CT. This one is S instead of X. And then I can select my standard. It's by default selecting the American standard. I can click on it. And you can see here I have the 2 American standard, the IEEE's one, and also the IEC standard, the 2 old one and the latest version. So I'm going to select the latest version. And then this CT that I'm having, it's a protection CT. If we go back to the nameplate, it's a 5P10 CT. So I'm going based on that. 5P10 means a protection CT. So let's go back to our MVCT. So it's a protection CT. Sorry. And the accuracy class for it is 5B. So you have all the classification that we have talked about, the 2B, 5B, PR classification, and also the BX and the TBX, Y, and Z, which is the transient-based classification. For us today, here is the 5B. I have to define the volt ampere, it's 5. And the accuracy limiting factor is 10. So 5P10. If you want, you can throw the actual burden connected to the CT once you measure it as well to do a calculation based on that actual burden. Let's define this to be 2. Now, the only thing left for me is to define the ratio on the top and the below here. So I put the primary value here. It's 300. And the secondary value is 5. Either 1 or 5. Usually these 2 value. I can add as well the manufacturer of this CT, the serial number, and so on. So manufacturer, for example, Megger. The serial number is 1, 2, 3. Asset ID and which phase A. This is more of an informational things to display in the CT. Another 2 options we have here is if your CT is connected to a transformer and it's buried in a delta connection for the primary side, you can enable this option. It will apply a factor 2/3 to that CT. If your CT is connected in GIS systems, in GIS systems, sometimes you have to swap the leads when you're testing CTs. You can simulate that primary lead swap using this option as well. So with that, we have finished all the information we need for our CT. You can see there are some small spaces here for us. These spaces are if you are defining a TBX, TBY, or TBZ CTs, some additional parameters like the transient or transient primary, coefficient or time constant TB, TB, TS required will be shown in this area. So I'm going to click OK. And then I can run my test. I can start with the winding resistance, then go to saturation, and then ratio. And of course, always start with the insulation test. Or I can just run all tests here that give me an easy way to do that. I can tick all my saturation, ratio, and winding. If you have multiple tabs, it will show here for you, and you can select all of them using these buttons. If you have multiple tabs, it will give you the option either to do it concurrent or without concurrent. In addition to do that as well, I'm going to throw another also an insulation resistance test, secondary to ground test. Now, once I do all of that, I can just click start. It will give me a window showcasing for me the connection that is required to be done. And this connection will change based on the number of tabs on the CT. So if you have multiple tabs, this connection will be shown for you. You have two cables, a blue one. I can zoom out a little bit. A blue and the green one. These two cables, one for the secondary and one for the primary of the CT. And they are very long cables. You can see here. I have the primary cable and the secondary cable here for me. And the secondary cable have 5 terminals. 3 out of them is not connected at the moment because I have only 2 tabs on my CT. So to minimize any error in the connection, it's also shown for you before you start to verify that you have this connection on your CT. So we have all that done. Just click start and the test will begin. For us here, I'm only going to do secondary to ground since I don't have a primary. This is a window type CT. I don't need to do primary to secondary or primary to ground test. I don't see any question being asked in the question page. I hope everything is clear and easy to understand. If you have any question, please feel free. And usually when there is no question means that everybody is understanding everything or nobody is understanding anything. I hope it's not the second case, it's the first one. So usually the testing insulation test is done with 1 minute value to give you the value for it. Can you see here it's 16.5 giga ohm. It will automatically go to the second test, starting with the winding resistance. And as same order as I mentioned, winding resistance, demagnetization, saturation, and then the last it will be the ratio test. So this is the demagnetization process. It's going through the cycle of slowly demagnetizing your CT. This is just a graphical representation of what's actually happening the CT. Once it reaches a very low value, it will stop. Then the saturation test. Here I selected the DC method, so it will show me the DC method. But if you want, the MVCT can go even up to 300 volt for doing a saturation test. And at the end of that saturation test, it will automatically start another demagnetization of the saturated core. On the value 14 volt. Then the ratio test is done using the voltage method, where we inject the voltage on the secondary. It's 10 volt or almost 11 volt, and voltage measured from the primary is shown with the test current as well. Usually the voltage test or the ratio test is done on the linear range of your saturation curve. Once it's finished, it will give you the test report. Let's go through the test report and see what do we have here. So the first thing you can see is the nameplate information. You can use the knob here below to scroll down, or you can scroll it down like this. So here you can see the information regarding the nameplate and the value. Let's zoom in more to give you a better picture of that. This is the maximum zone of the camera. So I have my nameplate value 300 to 5, and then I have the measured value 300.03625. This is how much error, what is the test voltage, test current, and the measured primary voltage. Then I have the knee point test. The knee point was found at 14.429 based on the standard measured test, and the current 0.707 ampere. Also the phase deviation, this is the phase deviation between the primary and the secondary, it's 0.3, and the polarity is, because the phase deviation is almost zero, the polarity is directly measured as correct polarity. And last we have the winding resistance value 0.086. You can define a temperature correction for that if you like in the setting page. Then you have the core or the saturation core graph showing you all the data you need, and the measured value from that graph regarding the inductances LM, LS, and TS as well. In addition to that, you have the values for the ratio and phase error table. You can see these values at different rated current. Even though we did the voltage method, it still calculated all of this using some sort of modeling for different rated currents at different burdens. If we have put the actual burden value, if you remember in the nameplate, it will add another measurement for the actual rated value to see what is the exact error at that rated burden as well. Also, we have a second page here. Click on it. It will show you an additional graph for the phase displacement error and graphs for the error at the percentage levels. And at the end, it will give you some assessments. It will calculate for you the ALF. It's the accuracy limiting factor. It's 17.6, which is above 10, indicating that the CT is within its accuracy limiting factor. So you have 5% error at almost 17.5, which is above 10. So this CT is okay. The ratio for this CT at the normal rated current is also within error. Also the phase. So all the classification and everything has passed. If anything failed, it will show you fail, means this CT is out of specification. And you can save this report at the end and put your logos on the report, and then save this report directly to a flash drive to the screen and get it as either PDF or the actual test format, the PowerDB format of the test report itself. So that will be all for the demo of the CT. So let me share my screen again. So if you are interested in doing conventional testing method, we still have a solution for you. If you want to do the primary injection and voltage injection, we have tracks, our substation and transformer test system that you can use to do all the other tests that have been done, but more of a manual way or in a primary method way. We have the Odin. It's a primary injection system usually used for low voltage circuit breaker testing, but you can use it as a primary injection for CT testing as well. You have a Magnus. This device, it's also a manual device that can do a new point test for a very high voltage values. Have the Ingevar. It's a mini version of the Odin to do primary injection as well. And of course, last but not least, you have the 5 kV insulation resistance tester. You can do the insulation resistance testing with them. I would like to thank you very much for joining us on this session, and I hope it's been a beneficial session for you. And now we will answer any question that you may have during the session. Unfortunately, I don't see any questions being asked in the session here. I hope that's everything is understandable, and the lack of questions does tell me either everyone is understanding everything or no one is understanding anything at all. I hope it's not the second case. I hope my voice was clear throughout the presentation. If anyone had any breaking issues during the session, please tell me, and if you want, I can repeat any points that have been missed and explain it further to you directly to you. One thing I forget to mention here is that I'm going to write my email address in case anyone have a question later on or would like to know about anything. I am always available for you to ask a question for it. And if anyone wants this presentation, please feel free. I can send you a copy of the presentation itself. Okay, then. I do apologize that I have exceeded the time limit by 20 minutes. Sanjay, would you like to say any closing thing before we start, before we end the session? Please feel free to do that. Thank you all for joining us, and I hope you have a nice day.